All right, let's look at another one, another example. So this is what's the maximum speed that a car can make around a turn given a given radius of the turn on a level road, so unbanked. That means that it's not slanted, it's just a flat road without sliding. The radius is what you expect. Okay, so what we have is we're going to have a curved road like this. We're looking at it from above. And so this car is coming around and it's going to make this turn. The radius of the turn is 20 meters. Well, we want to know what's the velocity, what's the maximum velocity this car can go, given that the mass of the car is 1,500 kilograms. And that's it. Okay, so this is the top view. If we go to the side, or rather behind, that's how I like to think about it. So if we're looking from behind, now this example, I'm doing it a little different than what they do in the text. But imagine it's going into the page, into the screen, and so it's kind of following, a circular path like that into the screen. So we want to analyze the forces. So we're going to have some weight and a normal force here. And then since it's turning at constant speed, although it doesn't say that, it's just saying what's the maximum speed. We're going to have some centripetal acceleration towards the center in this direction. So I need a net force. I need the centripetal force. And the key here is that when you turn in a car, it's actually static friction. You have to understand, like, you turn your wheels. So here's a wheel. And so if I turn my wheel, it's not sliding this way, right? It's going this way. And so it's this pushback. And so what we end up getting is we get a static friction force that's pushing us this way. It's keeping us from trying to go in this direction, out of the circle. So this is key. It's not kinetic friction. That's what there's always confusion about that. If you overcome the static friction, you're going to slide off the road. Okay, so it's static friction. So my centripetal force is going to be a static frictional force. I'll go ahead and write that here. So it's equal to static friction. All right, so let's begin analyzing this. So my centripetal force is equal to the mass times the centripetal acceleration. This is how you always want to start this thing, no matter what we want to determine. So I want to know speed, so I need to get velocity in here, and so that's going to be in the acceleration. So we know that the centripetal force is equal to the mass, and then centripetal acceleration is just v squared over r. So now I have my v, I know r, I know the mass. The centripetal force, well, centripetal force, we said, is going to be the static frictional force. So that's equal to m times v squared over r. And then thinking back, it's like, okay, my static friction force, I can calculate that by doing the coefficient of static friction times the normal, which is equal to m times v squared over r. Okay, so this coefficient, since it's rubber on concrete, we're going to say that the coefficient of static friction can be 1. That's as high as we can go. It doesn't matter, though. It could be 0.8, 0.9. It doesn't matter. Process is the same. Normal force. Okay, so the normal force, if we look, we see that this one and this one, there's no motion in the y direction. So the normal is equal to the weight, but the weight is equal to mg. So I can substitute the normal is equal to mg. So I get coefficient of static friction times mg equals mass times v squared over r. Now we know everything, so now we can solve. So again, my target variable is the v. So first thing we'll see is that mass cancels out. So that's interesting. So on a road, if you're a road engineer, you don't care about the mass of the vehicles. All we care about is the speed at which it moves. And so we get coefficient of static friction times g is equal to v squared over r. If I just multiply the r to the other side, I get coefficient of static times g times r is equal to v squared, so I take the square root on the other side, and that is my maximum speed. This is how fast I can go without overcoming the static friction. And so we can just plug in our numbers. I'm not going to do that. What I want to see is that, it's only dependent on the coefficient of friction and the turn, the radius. So as this goes down, this also goes down. So if you have a really tight turn, you need to go slower. And that just makes sense. A nice long banked curve, you can go a lot faster. So on the interstate, you'll notice that it's much larger radius turns than on a city street where the speed limit is much lower. So that's it. We're going to be this over and over again, being able to deal with this.